Welcome back. In this video, we'll finish up chapter 13 by discussing the Diels Alder reaction, which is a 1,4 cycloaddition reaction of dienes. So in the Diels Alder reaction, we're looking at the reaction of a diene with a dienophile. Now a diene must be a 1,3 diene. So it's a conjugated diene. That's really important for this. The dienophile is any double bond, any other double bond. A diene, the reaction of a diene and a dienophile will yield what we call an adduct. The adduct will always have this cyclohexene ring. So this is, notice this is cyclohexene. Now as we add more and more substituents to the diene or the dienophile, the structure of this adduct is going to become more and more complex. The mechanism for this reaction is often drawn in this way. We imagine forming a new bond between this carbon and this carbon, the bottom carbon of the diene and the bottom carbon of the dienophile. So we're making a bond to this carbon. We'll need to break a bond from that carbon. We're making a bond from this carbon to that carbon. We'll have to break a bond at this carbon. And it doesn't matter if you show your arrows going clockwise or counterclockwise. And of course, this is just an error that my screen does in PowerPoint. But you can show your arrows going clockwise or counterclockwise. It doesn't matter because it's a concerted reaction. The mechanism here, it happens all at once. And that actually is going to have important implications for stereochemistry. Sometimes you'll see the Diels Alder reaction called a 4+2 cycloaddition. What that means is that one of the reactants has 4 pi electrons. Here they are, 4 pi electrons. And the other one has 2 pi electrons. That's all that means, a 4+2 cycloaddition. There are other cycloadditions, but we won't learn about those in this course. In this course, we're going to focus on the Diels Alder reaction. Okay, so a common diene, of course, is going to be 1,3-butadiene. We'll look at more reactive dienes in this course, but really, we'll learn about more reactive dienes in this section, but really, 1,3-butadiene is sort of your standard go-to diene for all of your diene needs. Anyway, maleic anhydride ends up being an excellent dienophile. Not only does it have this double bond, which is a requirement for a dienophile, it also has electron withdrawing groups, which we will see aids in the reaction of dienes with dienophiles. So if I want to predict the product of this reaction, I can do this one of two ways. I could just draw my curved arrows this way. And then if you read those curved arrows, you can see that this is a new bond, this is a new bond, and we've moved the pi bond. Or I can use the dashed lines as I did previously and draw it that way. So let me just do this, just so I'm being clear about what I mean here. Well, apparently not. All right, we'll do this then. Okay, so the other way to draw the mechanism, so both of these will be in the slides. Is like this. Either of those approaches is acceptable. So our diene reacts with our dienophile, forms an adduct. The adduct has a cyclohexene ring. The adduct will always have a cyclohexene ring. Notice that all you have to do for this reaction is heat it. There's no catalyst required, nothing else. These are actually equilibrium reactions. Some Diels Alder adducts will degrade upon heating. Some will preferentially form. It depends on the relative stabilities. So what factors favor or disfavor the Diels Alder reaction? Typically speaking, in a normal Diels Alder reaction, it's important that we identify we're talking about a normal Diels Alder reaction. The diene is electron rich. And the dienophile is electron poor. And what that means is that the diene has an electron donating group or multiple electron donating groups attached. So we have these electron donating groups on the diene which help to add electron density to this conjugated system and make it more reactive. Similarly, on the dienophile, we have an electron withdrawing group. We have one or more electron withdrawing groups that pull electron density away from this pi system and make it more susceptible to attack. So you can think of the diene as being more like the nucleophile and the dienophile as being the electrophile. And in this case, you can have, in type A, what they're labeling as type A, we have the electron donating group at carbon 1 of the diene. In type B, it's at carbon 2. So is it at a terminal carbon of the diene, or is it at an internal carbon of the diene? In either case, we could predict our product. By drawing a mechanism, and we note we form a cyclohexene ring. Notice that this is the new bond that forms right here, and the electron donating group and electron withdrawing group are in those positions. Similarly, for this case, and I'll draw my mechanism using the other approach here. Similarly, in this case, we have our electron donating group and our electron withdrawing group. They are at 1 and 4 positions on the resulting cyclohexene ring. This is what we call a normal Diels Alder reaction. There's also what's called inverse electron demand Diels Alder, where you have an electron poor diene, an electron rich dienophile, but those are less common than this situation, what we call a normal situation, where we have an electron rich diene. So electron donating group is going to donate electron density to diene, and an electron poor dienophile. Okay, so these are the inverse electron demand Diels Alder reactions, where we have an electron withdrawing group in the diene and an electron donating group in the dienophile. Like I said, these are less common, but in the end, you can draw the products the same way. Just by trusting your mechanism. All right. Let's talk about relative rates for Diels Alder reactions. So the reaction of a diene with a given substrate to form a Diels Alder cycloadduct. So we're going to take a given dienophile and change the diene. This is imagine doing this series of experiments. You go in the lab, you start out with maleic anhydride, and you are going to react this dienophile with a series of dienes. So we have diene on the left, diene in the middle, and diene on the right. And we can see that the 1,3-butadiene, the reaction takes 4 hours to go to completion. So excuse me, that's the half-life, or the T1 half. There you go. That's what I want. So this is 4 hours to go to completion. 4 hours to reach 50% conversion. Sorry, I don't know why I was struggling with that. All right, so anyway, this reactant takes 70 minutes, and this one takes 20. Well, what's changing in this series? Here, we have a hydrogen atom. If we think about the carbon-hydrogen bond, it's generally considered nonpolar. If we have to commit to it being polar or nonpolar, or if we have to think about a bond dipole here, hydrogen is a little bit less electronegative than carbon. So you can think of that as being a little bit electron donating, but we know that alkyl groups are significantly electron donating. We think of alkyl groups as electron donating groups. Here we have lone pairs, and those lone pairs are going to allow this oxygen atom to donate electron density. Yes, it's true, oxygen is more electronegative than carbon, and just based on an inductive argument, you would expect oxygen to take electron density away. But that lone pair there, those lone pairs, allow you to draw resonance structures which actually put negative charge at different positions on the ring. We can draw a resonance structure that puts a negative charge here, and a resonance structure that puts a negative charge here. Now we can look at the dienophile. So for a given diene, we can change the dienophile and see how changing its structure affects reaction rate. We can see the slowest reaction occurs with only one electron withdrawing group. 2 electron withdrawing groups speeds it up more, or speeds it up, and then 4 electron withdrawing groups makes this reaction occur very, very quickly. Steric effects also play a role. So previously we were looking at electronic effects. We said that we wanted electron-rich dienes and electron-poor dienophiles. For steric effects, we want to minimize anything that's going to prevent the diene and the dienophile from approaching each other in the appropriate conformation. So for the dienophile, it's simple. The more bulk you put onto this molecule, then the harder it is going to be for the reaction to occur. It's going to be harder and harder to get the diene and the dienophile to align in the correct geometry for the reaction to occur. So now we're talking about stereochemistry of the Diels Alder reaction. So before we do that, I want to go back a little bit, a couple of things I feel like we could have talked about here. And we will add in a slide. And we'll go back to, yeah, we'll add in a slide right here. Okay. Okay, so when I was talking about the electron-rich diene with the methoxy group attached, I mentioned that these lone pairs really matter. So why is that? Well, we can draw a resonance structure which is negative charge on this carbon atom. Ignore those weird PowerPoint errors. And then we have another resonance structure that we can draw. That puts negative charge on this carbon atom. So we can think about this diene as being more electron rich than just regular 1,3-butadiene, because there are no resonance structures that I can draw that put more electron density on one of these 4 carbons without putting less electron density on one of the other ones. Here, I was able to bring more electron density into one of these carbon atoms because I put the positive charge outside of the diene, outside of the 4 carbons that will participate in the Diels Alder reaction. That's what we're thinking about. We're thinking about the reactivity of the carbon atoms that will participate in the reaction. Okay, that was one piece. Another piece is relative reaction rates of dienes. When we think about dienes, the ability to adopt an S-cis conformation becomes important. And we'll talk a little bit more about this later. But while we're talking about relative rates, if we think about butadiene, then it turns out that cyclopentadiene reacts much more quickly than butadiene, which reacts much more quickly than this diene. And why is that? Well, it turns out that for the Diels Alder reaction, and like I said, we'll talk a little bit more about this, so we'll talk more about this as we go forward. For the Diels Alder reaction, you have to have your diene in what we call an S-cis conformation. So let me just refresh on that. This is what we call S-cis, and this is S-trans. So you can see that in the S-trans conformation, there's going to be less steric interaction of these hydrogen atoms here and here, whereas there's more steric interaction here and here of those hydrogen atoms. So the S-trans conformation is generally more stable, but there's an equilibrium between the two. and the S-cis conformation can exist for some amount of time, or does exist for some amount of time before going back to the S-trans. So they're constantly going back to the solution. You have a dynamic equilibrium set up, and the more time the molecule spends in the S-cis conformation, then the more likely that it will be in that conformation when the diene collides with the dienophile. So now let's go back up here and look at these three. In the case of cyclopentadiene, it's stuck. It's permanently fixed in an S-cis conformation. There's no way for it to rotate to an S-trans conformation. So by being permanently fixed in an S-cis conformation, it's always ready to do a Diels Alder reaction. In fact, cyclopentadiene is so reactive that when you purchase it, if you want to use cyclopentadiene as this exact molecule, then you have to heat it to break up the adduct that forms in solution. It actually forms an adduct with itself, or one molecule can act as a diene and another molecule can act as a dienophile. Cyclobutadiene is going to, or not cyclobutadiene, 1,3-butadiene is going to be sort of our standard that we compare all other dienes to. And you can see this diene, we've added some sterics here, making it even less likely that it'll be in the S-cis conformation, giving it more steric hindrance in the S-cis conformation, driving it towards an S-trans conformation. And I just wanted to say, before we move on, that in order for this reaction to occur, the diene has to be in an S-cis conformation so that these carbon atoms can align. Another way to visualize that would be, we've been drawing our Diels Alder reactions like this, our mechanisms like this, and you can imagine that we're just not in the right conformation at this point for this reaction to occur. Remember that it's concerted. All of those bonds are being made at the same time. All right, moving on. Stereochemistry of the Diels Alder reaction. This is one of the reasons why the Diels Alder reaction is so widely celebrated and widely used. The Diels Alder reaction is stereospecific. It gives you a syn addition, and you're forming multiple new carbon bonds at the exact same time. You actually fix the stereochemistry of 4 carbon atoms simultaneously. The configuration of the dienophile is retained in the product. What that means is that in this case we have cis dienophile. This is dimethyl malleate, but this is a cis dienophile, meaning that the 2 ester groups are on the same side of the double bond. They're cis to one another. When we form our cyclohexene adduct, they will still be cis to one another. They'll be on the same face of the ring. So if they are on the same side of the diene, they'll be on the same face of the ring in the adduct. So here we have a trans dienophile. I believe I said diene back here, I meant dienophile. If we have a trans dienophile, then our adduct, after reaction with the diene, is going to be a trans adduct. Now, in this case, this molecule is chiral, so we would expect a racemic mixture. Only one molecule is shown here, but it's implied that it's a racemic mixture. So do keep that in mind. We always do form pairs of enantiomers. The diene reacts in the S-cis rather than the S-trans conformation. So that's what I talked a bit about a minute ago. If you try to draw a trans double bond in a 6-membered ring, you're going to end up with a silly situation like this. If you try to make the model from your kit, you're going to either not be able to make it or you're going to break something. So the geometry just doesn't work for these 109.5 degree bond angles here and 120 bond degree angle here. It just doesn't work if you have 1, 2, 3, 4 atoms, these 2 atoms as far away from each other as far as they can be. There's no way to get the rest of the ring connected. In fact, you can only have a trans double bond once you get up to about 8 carbons in the ring. And we're only forming cyclohexene rings. Only 6 carbons will ever be formed in these Diels Alder rings. Okay, this is the case we were talking about earlier. If the diene is locked in the S-cis conformation, the reaction occurs very quickly with no issue. If the diene is locked in an S-trans conformation, this reaction cannot occur. No reaction. So this has to be able to adopt an S-cis conformation, and this diene never will be able to adopt an S-cis conformation. So cyclic dienes in which double bonds are held in S-cis are usually highly reactive. So here we have maleic anhydride, And we're back to cyclopentadiene. So think of cyclopentadiene as your very, very reactive diene. This diene with two exo double bonds that are stuck in an S-cis conformation also reacts very quickly. And then, of course, we use 1,3-butadiene as the standard that we compare all other dienes to. When forming our products, the endo product rather than the exo product is generally preferred. So whenever we have to decide which product we're going to form, if we form a bicyclic ring system, we're going to find the endo product is more favored. So here, there's a couple of ways to look at this. So this is a bicyclic ring system, and you have a 6-membered ring. That's your longest bridge, or rather you could say a 2-carbon bridge and a 1-carbon bridge. That's probably the easiest way to do it. Here's 1 carbon in this bridge, here's 2 carbons in this bridge. Think back to naming fused ring systems or bicyclic structures in the first semester of organic chemistry. We would name this by counting all the carbons. So this would be bicycloheptane, because there are 7 carbons total. We call this carbon here and this carbon here bridgeheads. All the other carbon atoms are bridges. So there's a 1-carbon bridge, a 2-carbon bridge, and a 2-carbon bridge. So this was 2,2,1 heptane, bicyclo-2,2,1 heptane. Well, in this case, you're asking the question, okay, when we add our R group, once we form our adduct, our R group has to make a choice between being closer to the shorter bridge or closer to the longer bridge. If it's pointed towards the longer bridge, meaning it's closer to this bridge here, pointed downward, then we say it's endo. If it's pointed towards the shorter bridge, we say it's exo. The endo product is preferred. It's called the Alder endo rule. The Alder endo rule. And you'll read about that in your text. So, long story short, when you hear Diels Alder, think diene, dienophile. If you have to pick, it's going to be the endo product, not the exo product. And then it turns out to be kinetically controlled. Excuse me. So if a dienophile contains activating groups with pi bonds, they prefer the endo orientation in the transition state. This is what we mean by kinetically controlled. Factors that affect the transition state affect kinetics, affect reaction rate. So whenever we form the endo product, the product that puts the group with pi electrons, or pi bonds, same thing, on the endo side of the bicyclic structure, you can see that they sort of fall underneath the pi system. So these two X groups were underneath these 2 pi bonds when the ring formed. They weren't facing away in this direction out towards the smaller bridge. And this has to do with something we call secondary orbital overlap, which we'll talk about a little bit more in a bit. But so how do we use the Alder-Endo rule? Well, given these 2 molecules and asked to predict what the product would be, you would expect to form the endo product, not the exo product. What I mean is that you would form this product here, this endo product as drawn, and you would not form the product with, and this is going to be a little funky to draw, a little bit hard to draw, but we'll get there. You would not form this product, which is exo. Okay. We say it's a stereospecific reaction, as we mentioned earlier. When the Diels Alder reaction occurs, we have retention of configuration in the dienophile, meaning that here the 2 X groups were cis to one another, so they're cis in the cyclohexene adduct. If they start out trans to one another, then they will end trans to each other. Whoops. in the cyclohexene adduct. Similarly, if the diene has functional groups that are on the same, or well, the stereochemistry of the functional groups on the diene will affect the stereochemistry of the functional groups in the product. And at this point, I think it's helpful to use a little trick. We use what's called the cube rule. So let's go ahead and take a look at that handout now before we go any further into this, because I think the stereochemical outcome can be very difficult to see without some extra help. So if you go onto Blackboard, you'll find a handout that looks like this. And this is just something I modified from, that I found online and then modified to make it fit the content of our course. So whenever we have a diene and a dienophile coming together and we're making a choice between endo and exo products, we're interested in the secondary orbital overlap. As groups C and D are in the dienophile, as groups C and D approach the diene, if these groups C and D have pi electrons, then it's going to be beneficial for those p orbitals to overlap with the p orbitals in the diene. That's what sets you up for putting the C and the D underneath the diene and gets you the endo product. This concept, secondary orbital overlap. This cube method is a nice trick for determining the stereochemistry in your product, for determining what it's going to look like when both the diene and the dienophile have functional groups, or substituents. Substituents is a better way of saying that. Particularly when there are substituents at carbons 1 and 4 of the diene. So imagine drawing a cube. The diene goes on top, and with its carbon-carbon bond on the left side. The dienophile goes on the bottom with its carbon-carbon double bond on the right side. Then we're going to put groups C and D, if they exist, at those corners of the cube. Then you imagine forming your new bonds where you see these orange lines. Don't forget the other substituents are present. See how they've drawn the hydrogen straight out? That's very helpful for predicting the structure, because in the end, once you have your new bonds, you can see the stereochemistry. All 4 of these hydrogen atoms are on the same face of the ring. All 4 of the hydrogen atoms are on the same face of the ring. And this takes some practice to use, but once you get used to using the cube method, I find that it's incredibly easy. Without the cube method, it requires a little bit of brain energy. Sometimes you have that, sometimes you don't. Probably depends partly on how much breakfast or sleep you had. But instead of depending on being able to visualize it, I much rather have a systematic approach that I can go through. And definitely this cube method is handy for that. I draw a cube, I put the diene at the top, dienophile at the bottom. I make sure I pay attention to secondary orbital overlap. I put my C and D groups under the diene. And then I just look at the stereochemistry at that point, and that tells me what the stereochemistry of my product is going to be. So let's go back to our slides now and try to apply the cube method. Okay. So in the case of the top reaction, try to get my pen to work. There we go. In the case of the top reaction, I'm going to draw, well, let's just get our cube set up and then I'll edit it along the way. So there's our cube. I'm sure you've drawn cubes before. You know, you can draw 2 squares and just connect them diagonally. However you prefer to draw them. The diene is going to be the top part of this cube. The dienophile will be down here at the bottom right. My Y groups come out this way. Notice how I'm keeping all my lines parallel. This bond and this bond, this carbon Y bond, in each case is parallel. to the bond in the carbon-carbon bond in the dienophile. Now there is another bond here at this carbon atom that is going to hydrogen. Same here. Again, these bonds are parallel to other bonds in the cube, or at least I'm trying to make them parallel. And here we don't have to worry about secondary orbital overlap because all we have are hydrogen atoms bonded to our dienophile. But what this shows me is that, let me get a different color here. What this shows me is that all four of these hydrogen atoms are on one face of the cube that I'm drawing. The two Y groups and the other two hydrogen atoms are on the other face. And that means in our product, our two Y groups are going to be on the same face of the ring. If we try this again with the molecule shown at the bottom, and I'll draw my cube a little bit larger this time, or my parts of my cube. I don't actually end up drawing the whole cube out. One Y group is going away from the other pi bond. The other Y group is going to be closer to the pi bond. So remember that we have a group here, that's a hydrogen in this case, and then we put our other group here. It is important that you stick to this format, keeping all your bonds parallel in order to be able to see the stereochemistry. Again, hydrogen, 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 hydrogen. And now we can see that our Y groups are on different faces of the cube. So here I have hydrogen, Y, hydrogen, hydrogen, all on one face, and then the other Y group is on the other face of the ring, and that's what we observe in our product. Just going back to the cube, in case it's hard to see, I know that when you're first doing this, where's the cube is a common question. I don't see the cube. The cube is, its top face is here. Its bottom face is here. This is the bond that you're forming. And then this makes up the other wall of the cube. So here are some examples. In this case, it doesn't really matter what you do because there's so much symmetry in the dienophile, and there's only one group on your diene. And if you're ever in doubt, what I would do here is draw your cyclohexene adduct, because we know this is always going to form a cyclohexene adduct. This is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm going to put my methyl group here, and then I'll add my cyano groups. And I can see that it doesn't really matter which side of the ring I put this on because I know I'm going to form a pair of enantiomers. At the bottom, the same is going to be true. There's so much symmetry in the product that it really just doesn't matter where you put them. And in these cases where you don't have to worry about stereochemistry, you don't need to worry about the cube method. That's not going to end up being relevant. Okay. So remember that when we talked about electron donating groups, they have a big impact on rate. Sterics also has a large impact on rate. And whenever the two compete, then sterics will end up winning more often than not. So if the molecule can't adopt the S-cis conformation or rarely adopts the S-cis conformation, then it matters less how reactive it is once it gets there. So sterics, in this case, indicate that we're going to disfavor the S-cis conformation. Electronics suggests that we have two electron donating groups, so that should accelerate the rate of the reaction. But as I mentioned a moment ago, sterics end up dominating in this case. We end up adopting the S-trans conformation, which is unreactive more often than not. Or the S-trans is always unreactive. We end up adopting this conformation more often than not. Okay. So a couple of examples for Diels Alder. Again, we're using maleic anhydride. Maleic anhydride is a very commonly seen, commonly used dienophile. It has those 2 electron withdrawing groups nearby, which help to make it electron poor. And if we look at the Diels Alder reaction for the tert butyl group as an R group versus no R group, definitely we expect the top one to react more quickly. Partly you could argue for electron donating reasons, but also for sterics. If you think about this tert butyl group swinging around, now it has to interact, this very large tert butyl group would have to interact with this CH2 group, which would be sterically demanding. So if a methyl group and a hydrogen have difficulty being close to each other, certainly a tert butyl group and a hydrogen are going to have a hard time being close to each other. All right. So this is just saying that diene C is faster than diene D. That's C and D. And then D is much faster than diene E. In this case, in order to adopt the S-cis conformation, we would have to put the 2 tert butyl groups cis to each other. And at this point, again, if you make the model of these, you'll see that you have some significant steric problems right here, where you're not going to be able to put those 2 hydrogens in the same place at the same time. So we always do want to consider sterics. They're going to be part of our consideration when we're looking at Diels Alder reactions to determine whether or not the diene can adopt the S-cis conformation. Okay, so how do we predict products? Well, we start by showing the diene in an S-cis conformation. You won't always be given the diene in an S-cis conformation. This is S-trans. It's up to you to know that this is only going to react if it can adopt the S-cis conformation. So you draw it in an S-cis conformation, ask yourself, is this a reasonable conformation for this molecule to obtain? And it is, in this case. So once you've determined that information, then you can show your arrow pushing mechanism and draw your product. Remember, our product is a cyclohexene adduct. How to use Diels Alder in retrosynthetic analysis? Well, if you want to consider a diene and a dienophile, there are a couple of ways you could do this. Whenever you see a cyclohexane or a cyclohexene ring, whenever you see cyclohexane or cyclohexene as a target molecule, so this molecule that I'm circling here would be our target, then you can imagine that it could have come from a Diels Alder reaction. So we could imagine this molecule having come from directly this diene and this dienophile. But it doesn't quite work out. These methyl groups don't have any pi electrons, so there's no reason for them to go. Sorry, I just had a moment there. So there's no reason for them to find their way under the ring. There's no reason for there's no secondary orbital overlap. That's what I'm looking for there. There's no secondary orbital overlap. There's nothing driving the Alder-Indo rule in this case. We're not going to get the product we're after. Plus the diene here, the diene is electron rich, but the dienophile is not electron poor. We want to put some electron withdrawing groups on it. So we see this molecule and we realize this could have come from a cyclohexene ring if we just reduce it. So if there were a double bond here, then we could imagine having reduced it. We can imagine a very simple case where we bring a diene and a dienophile together. We note that in this case our dienophile is not electron poor. So we start thinking about how it could have come from an electron poor dienophile. How can I convert what's methyl in our product to an electron withdrawing group? An aldehyde comes to mind. Here they use carboxylic acids. But how would we do that? Well, this could have come from this molecule, which could have come from this molecule, which could have come from this molecule, which could have come from these two molecules, which are what are shown over here. So the solution, remember we used the electron withdrawing groups on the dienophile to help facilitate the reaction. We talked about how using the methyl groups directly would be a much more difficult reaction to achieve. So here we have our diene and a dienophile. Dienophile has electron withdrawing groups. We form our product, and we can do a reduction to reduce the double bond and then the carboxylic acids to form this product. We're not quite to our desired target yet, so we convert our hydroxyl groups into bromo groups, and then we can convert these bromo groups to just CH bonds with lithium aluminum hydride. Okay, that's the end of chapter 13. What I think you should do at this point, because I know that where we typically have trouble is the jump from this point, I believe, to this point. To the point where you have to start figuring out whether the groups that were on the diene are going to be on the same face or opposite faces. And then you can get into situations where there are groups on both the diene and the dienophile, such as here. In this case, we have groups on both the diene and the dienophile. When you have functional groups on both the diene and the dienophile, that's when I want you to go to this handout that's on Blackboard and use the cube method. Get some practice using the cube method. If you go into your textbook, there are some examples that explicitly talk about the Indo rule and how to determine which products will form. And the information that you'll want to see for that when you're ready for it is on page 612 of Solomon's 11th edition. So page 612, 613, and then it goes on from there to talk about how to use Diels Alder reactions in a retrosynthesis. So I would not try to start with the cube method. Don't try to start with retrosynthesis or anything like that. Get really, really comfortable with this idea, this basic idea that a diene reacts with a dienophile and forms a cyclohexene adduct. Diene reacts with dienophile, forms a cyclohexene adduct. Once you're used to seeing that, then it just becomes a matter of, okay, where do I put these groups? What is their relative stereochemistry after the reaction? All right, that's it for this video. Next time we'll start on chapter 14.